The simulation window allows a means of testing and verifying the functionality of a program before going live with real hardware in a production environment. The simulation workspace shows the status of the program ins and outs as dictated by simulated field input conditions. Before pressing play, open the IR functions on the left menu to modify the electromechanical nature of the simulated field input devices. This utility is the reason why I have a special fondness for the EATON easySoft programming software. A lot of the freely available demo software floating around does not allow a user to modify the electromechanical nature of the simulated field input devices and often restricts a user to normally open devices. Not easySoft though. This particular programming software allows 4 different types of simulated field input devices. A simulated field input device could be normally closed momentary contact, normally open momentary contact, normally closed maintain contact, or normally open maintain contact in nature. A momentary contact is symbolized with a straight bar on the operator, whereas a maintain contact is symbolized with angled bars on the operator. I know in the comments section I've indicated the devices attached to inputs I2 and I3 are momentary in nature. However, let's instantiate them as maintained contact devices for the purposes of this simulation, since it's easier for me to get a screen capture of the running simulation without having to keep one hand continually on the mouse. Here we've instantiated the simulated field input device attached to input I2 as a normally closed maintain contact button, and the simulated field input device attached to input I3 as a normally open maintain contact button. Recall that the electromechanical nature of a field input device has absolutely nothing to do with how that input is logically instantiated in the program. Recall that a make instruction disallows logical continuity when that input experiences logical 0 and allows logical continuity when that input experiences logical 1. As dictated by the electromechanical normally closed nature of the simulated field input device attached to input I2, the normally closed red push button, input I2 would experience a logical 1, and the make instruction would allow logical continuity when the simulated field input device is in its deactivated normally closed state. When placed in its activated open state, it would receive a logical 0 and disallow logical continuity. In contrast, as dictated by the electromechanical normally open nature of the simulated field input device attached to input I3, the normally open green push button, input I3 would experience a logical 0 and disallow logical continuity when the simulated field input device is in its deactivated normally open state. When placed in its activated closed state, it would receive a logical 1 and allow logical continuity. Start thinking now how output Q1 should respond to 4 different input scenarios. 1. When both simulated field input devices are in their deactivated states. 2. When only the normally closed red push button attached to input I2 is actuated. 3. When only the normally open green push button attached to input I3 is actuated. And finally 4. When both buttons are actuated. If you're tracking, you should anticipate output Q1 to be asserted when only the normally open green push button attached to input I3 is actuated. Let's see if the simulation verifies our hypothesis. Expand the Input I menu to gain access to the simulated field input switches. Note the schematic symbols of the simulated field input devices change to represent those selected in the IR function menu. Input I2 as a simulated normally closed maintain field input, and input 3 as a simulated normally open maintain field input. Press play to begin the simulation. When neither button is actuated, the simulation utility indicates the make instruction examining I2 permits logical continuity. However, I3 does not permit logical continuity onto the output, and output coil Q1 is de-energized. You'll note the simulation utility symbolizes logical continuity by highlighting the active portion of a rung in bold red. When only the simulated field input device attached to input I2, the normally closed red push button, is actuated, the simulation utility indicates the make instruction examining I2 does not permit logical continuity onto the output, and output coil Q1 is de-energized. When only the simulated field input device attached to input I3, the normally open green push button, is actuated, the simulation utility indicates the series connection of the make instructions examining both inputs I2 and I3 permit logical continuity onto the output, and output coil Q1 is energized. When both the simulated field input devices are actuated, the simulation utility indicates the make instruction examining input I2 does not permit logical continuity onto the output regardless of the status of input I3, and output coil Q1 is de-energized. The simulation utility has thus verified the functionality of our program in response to our intended field input devices. We can now save the program if we haven't done so already and transfer it to a device. To transfer the program to a device, power up the EZ512 Intelligent Relay, place it in stop mode, and return to the status window. Open the port on the front of the device and install the communications cable and plug the other end into your computer's USB port. Open the communications window and then expand the connection menu. Choose the COM port used by the EZ512 Intelligent Relay using the drop-down interface menu. Press the online function to connect the device to the PC. Once connection is established, expand Program/Configuration and press PC to Device to transfer the program from the PC to the PLC. The easySoft programming software now writes the contents of the active program onto the device. Note, while connection is established to an actual device containing a valid program, one can remotely control and monitor the device's response to real-world field input devices. To do so, one must press Run and the Status Display button. The status display is this program's means of remotely monitoring an actual system in operation. Note, when neither button is actuated, the remote monitoring utility indicates the make instruction examining I2 permits logical continuity. However, I3 does not permit logical continuity onto the output, and output coil Q1 is de-energized. You'll note the remote monitoring utility symbolizes logical continuity by highlighting the active portion of a rung in bold red. When only the field input device attached to input I2, the normally closed red push button, is actuated, the remote monitoring utility indicates the make instruction examining I2 does not permit logical continuity onto the output, and output coil Q1 is de-energized. When only the field input device attached to input I3, the normally open green push button, is actuated, the remote monitoring utility indicates the series connection of the make instructions examining both inputs I2 and I3 permit logical continuity onto the output, and output coil Q1 is energized. When both the field input devices are actuated, the remote monitoring utility indicates the make instruction examining I2 does not permit logical continuity onto the output regardless of the status of I3, and output coil Q1 is de-energized. This remotely monitored PLC is behaving as anticipated to real-world field input. We can be reasonably certain this program will function as intended, and the communication link can be broken by going offline and the PLC placed in service by entering run mode. Alright, this about wraps up our brief introduction to the EATON easySoft programming software. We familiarized ourselves with the software environment and used the software to write, save, edit, and manage programs, simulate programs, transfer programs to a device, and monitor a device running a program. Not only does the use of programming software like easySoft greatly simplify the program entry and editing process, the ability to work on a program offline without stopping the PLC reduces production downtime. Additionally, simulation makes it possible to test and verify functionality before going live with real-world hardware in a production environment. We'll be making use of this software in later applications exercises to build and test some representative PLC programs. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.